So far, if you remember, we have been talking about the electrostatics of p-n junctions. So what happens when you bring a p-type material and an n-type material together? How do the charges redistribute themselves under equilibrium conditions? We haven't talked about current quite yet, although briefly we did last time. Okay? So the main purpose so far has been to understand the electrostatics. In other words, we were able to calculate how are the charges distributed here in the transition region or the depletion region. What is the field that develops across here, right? And we applied Poisson's equation, and we are able to explain all this fairly accurately. We make the assumption, which will become much more important today, that these regions outside this transition region are neutral. There are no charges. If there are no charges, of course, there's no field. Okay? But inside here, we have specific charges which are basically related to the uncompensated ions, the donor-acceptor ions. The donor ions have given away their electrons, so they're positively charged. Acceptor ions have accepted an electron, so they're negatively charged. Okay, that's what causes the charges here. And we also made the assumption that there are no carriers, no electrons and holes in this transition region. And that's an important assumption, and the physics behind the assumption is that if any carriers end up in this region, because of the strong field there, it'll get swept away really fast. Right? So that's pretty common sense, I guess. You can think about it that way. And the field, of course, is pointing from the positive charge to the negative charge. It is preventing the diffusion of the carriers. Okay? The holes try to diffuse from P to N, the electrons try to diffuse from N to P, and they're trying to balance, the built-in field tries to balance that out. So that's the equilibrium situation. Okay? And then we calculated what the contact potential is based on we can relate that to many things. First of all, the things that we cannot measure are, for instance, the width of the depletion, not easily measured, and the electric field. And you can relate that to the other constants here. At the end of the day, the width of the depletion region can be related to the donor-acceptor concentration. So we know that if the side that's more heavily doped will have a thinner depletion region, right? Because you need the higher concentration charges, which means you need a fewer distance in. The more lightly doped material will have a thicker depletion region. So the charges have to be matched. So the logic is important because you can look up the equations. It's not terribly important. Okay, so we can calculate all this, and here we can calculate how much it extends to each side. Xp naught is how much the depletion region extends to the P side. Xn naught is how much the depletion region extends to the N side. And the zero there represents equilibrium. Okay, so again, into which region will the depletion region penetrate more? If you can see it from this equation, if Na is much larger than Nd, you can see that Na over Nd will dominate here, and Xn naught will be large. Okay, so the P-type is more heavily doped than the N-type. The depletion region will extend more into the N-type. Okay, that's common sense now. What happens to the depletion region when voltage is applied? We briefly mentioned this. What happens is the band's bent. Your depletion region, if it's forward biased, the depletion region gets smaller. And the way to think about this is you can look at this equation. Okay, this W is the total width of the depletion region. Okay, forget everything else. Just look at the V. Okay, so W is directly proportional to the V naught. Now recall, V naught is the contact potential. Okay, when you apply a bias, that becomes, you will see, so at equilibrium it's proportional to that. Right? Forget all the other constants, not so important. When you apply a potential, you will see it becomes that. Basically. In other words, when V is positive, and we'll define this is P, that's N, that's positive. Positive terminal goes to P, negative terminal goes to N, it's positive. When V is positive, you can see the depletion region decreases because this potential decreases. You're decreasing the contact potential. When this V becomes negative, it's reverse bias. This whole thing increases, W increases, the depletion region increases. So you should have a good feeling for those things, and we'll reiterate that today. Okay, so this is where we stopped last time. Essentially, we looked at this example problem. Isn't that right? I make sure. Does someone remember?
We showed it to us, but we didn't work it.
Did you? Okay, so let's work this through, because then that'll be a review for whatever we did. Very quickly, actually. Okay? So this is the second example from the section. Says the junction described in example 5.1, which I have reproduced at the bottom, has circular cross-section with a diameter of 10 micron. Calculate x and naught, xp naught, q plus e naught for this junction at equilibrium 300K. Sketch ex and charge density scale. Okay. So that's the junction. So we don't need to actually work through this, because I'll work through this quickly, so we don't waste a lot of time. So essentially all we have the acceptor concentration here, we have the donor concentration here, so we know we have a transition region here. Okay? This whole width is W, this is xp naught, this width is xn naught. Okay, so basically you should be familiar with these in the notations, but I will, if I ask you a question, I will make it obvious what it is. Okay, so first calculate xn naught, xp naught. So the easiest ways, we just saw this, you can plug it in here. So first of all, if you look at this equation, you know ND, Na, epsilon is the dielectric permittivity, so you know that. Q is the electronic charge. V naught is the only thing you don't know. This is contact potential. You can easily calculate that from there. From here. Okay. So V naught, of course, is related to the doping on each side, so you can calculate it. Remember, this is the previous example that we solved. Okay. So remember, we had doping on each side. What is the contact potential? Okay. It's given by that equation, KT over Q ln Na and D over Ni squared. So you know the contact potential. Once you know the contact potential, you can plug this in here with the doping concentration, so you can calculate what xp naught is and xn naught is. Same thing. Okay, that's pretty straightforward. Okay. Now the next part of the question is what is Q plus? It is the total charge. Now remember, the total charge can be related, of course, to the contact potential as well and the field. So its expression is actually, let's see. The total charge, of course, is related to the concentration, right? So actually, you don't need to look up an equation. It should be pretty obvious. So you know the total charge on this side and this side are equal. Charge here is what? It is mostly the donor concentration, right? The donors who have donated the electrons. That's the unit charge per unit volume multiplied by the volume, right? What's the volume? It's the area, cross-sectional area, multiplied by the length. Okay? So it's pretty obvious. You don't need to actually remember anything. And the area, in this case, it assumes it's a square. It's just that, right? Radius squared of 4. Cross-sectional area is given. Okay, so that's the total charge. Positive charge is equal to the negative charge, so it's just one of those. Okay, the last part is the field. The field is given by that equation, right? So you just invert that. Field is 2V naught over W. Okay, pretty straightforward. Okay, so the last part is sketch the field. Oh, we've already done that. If you know the charge, to sketch the field is pretty straightforward. Okay, and I'll just show you the result here. You just do the integral of from the Poisson equation. Remember. Okay. So the field once you calculate the field, you just take the charge density on each side, and then do just an integral, just from the Poisson equation. Okay. Remember, the Poisson equation states that the change of charge density is proportional to the field. Right? No, sorry, a mistake. Change of field is proportional to the charge density. Okay. You should go back and review that from it's posted on the website. some background on the Poisson equation. Just comes from the very basic electrostatics. Okay, so this kind of stuff is basically electrostatics because no charges are moving. Okay, this is fixed. Okay, now we will talk about dynamics. When we actually apply voltage, charges will move, and that's current. Okay, that's the next emphasis of the lecture today. So let's get started. Okay. Oops. Well, actually, before I do that, there was one more thing I wanted to show you. Oops. There is a okay, close that. There is a very useful website which I'll post online, which has several applets which gives you a visualization of the different topics that we have talked about. So if you go to the main website, it's the University of Buffalo. There's a number of things. So for instance, you can everything from crystal structure to so let's look at what we just talked about, right? The p-n junction diode at equilibrium. So let's click on this. Okay. And it'll give you a sense for how things vary and how the different material parameters affect the fields and the potential and so on. So let's see. It should load. I checked it earlier, so I know it works. Okay, maybe give it one more shot. If not, then you guys can play with it yourself. But essentially, it simulates what the equations that we've talked about, and you can vary the different, donor concentration and the acceptor concentration, and see how things change. Like how does the depletion region change? How does the field change? How does the potential change, and so on. Look, it's a Java applet, and sometimes I remember that there was some issue with it not working, but okay. Anyway, I'll post it, and you should play with it, so you get a sense for the effect of the different parameters. Okay, so now let's talk about p-n junctions under bias. Okay, now we're going to introduce the concept of bias, which is basically what I just said here. Okay, you apply voltage to it, and it's assuming steady state in the sense that the voltage has been applied some time ago, and the whole system has reached some sort of steady state. So there's no transience involved here. We'll talk about transience later on. It's more complicated. This is the fundamental basis for almost most of the devices that we use today, including transistors, rectifiers, variable voltage capacitors, photocells, light emitters, everything. So it's quite important that we are able to understand how current is generated, the physics of how current is generated, and how do we calculate the current for a given bias voltage. This is the very basic understanding of devices. I would say this is the core part of the class to some extent, because once you know this really well, you can apply this to almost all the devices later on. Okay, so first let's concentrate on the junction. So because remember early on we said that there is no field outside here, so that should be relatively straightforward. If it's heavily doped, those are just majority carriers. Okay, and they just move basically, right? So we'll come back to that later on, at the end of this class. But let's focus on the junction. What happens to the current in the junction, essentially? Okay, so equilibrium, just to review, at V equals 0, we have some depletion region. The potential on the P side is different from the potential on the N side by a contact potential V0. The energy bands are bent like that, so the electrons have a barrier going this way, the holes have a barrier going this way. The Fermi level is constant throughout the material. Okay, pretty straightforward so far. The currents cancel out for each particle. Okay, so the particle flow is shown here, the current is shown here. The diffusion current of the hole and the drift current of the hole should cancel out. The diffusion current for the electron, the drift current for the electron should cancel out. They independently have to cancel. Okay, otherwise charge buildup will happen, right? Okay, once you have that, what happens when you apply voltage? Okay, so first, like I said, let's define what the bias voltages mean. Essentially, at equilibrium, no voltage is applied. In forward bias, you have an applied voltage of VF, where the positive terminal of the battery is connected to the P type of the material, the negative terminal of the battery connected to the N type. You can see this is the built-in field. When you apply a potential like that, okay, so let me draw this picture. So we have a battery connected to something. Which way is the field flowing? Just from the potential applied. This is positive, it's negative. Right? So this way. Okay. So when forward bias, the applied field opposes the built-in field. Remember, the built-in field is P%. Built-in field is from N to P. Remember? Right? Positive charge to negative charge. Okay? So in a forward bias, you will reduce the built-in field. The applied field is opposed to the built-in field. On the other hand, when you have negative bias, the opposite happens. Okay? This is negative, that's positive. The built-in field, the applied field is in the same direction as the built-in field. So you're increasing that reverse volt field. Okay? So you can see the other implication is that if you look at the depletion region, as you apply a forward bias, the depletion region gets smaller. And we'll see that why in a second. Okay? And you can imagine why, because you're reducing that built-in field, right? That total field has gone down. You can see it. It's smaller than that. Whereas in the case of reverse bias, you're increasing the depletion region because you're also increasing the built-in field. Okay? So this is the basic idea of what happens under different bias, and we'll understand why that is. So applied field opposes built-in field, and the net field decreases for forward bias. The opposite happens for reverse bias. Applied field is in the same direction as the built-in field, and the net field increases. The transition of the depletion region width decreases due to the smaller net field under forward bias, fewer uncompensated charges. Now, of course, what does that mean? That means that you have injected carriers from one side to the other side. Okay? When you have a field which is applied this way, the holes here can be injected to the N side. Okay? So you can see those regions which had uncompensated charges here now will have excess holes here. So this boundary will start moving this way. Okay? Another way to think about it is, remember, the built-in field was there because you had a diffusion current, right? You had holes diffusing from P to N type, and the built-in field was trying to prevent that diffusion. Now, the applied field is forcing that the equilibrium the other way. It is supporting that diffusion, right? Diffusion happens from P to N. The applied field is forward bias. Is also forcing it from P to N. Let's talk about holes. Okay. In other words, the built-in field, that built-in field is fixed, right? That comes just from the material properties, just from the doping. Nothing to do with this, the original field. Nothing to do with the applied voltage. So this whole thing has to reduce because you have fewer uncompensated charges. Same thing happens with electrons. Injection happens from the other side. Okay, we'll see that. For the reverse bias, the transition region width increases. And you can see this if you go back to our original equation by changing that V naught to V naught minus V, like we saw before. Okay? So to model it is pretty straightforward. Now let's look at the potential diagram. Not the energy band, the potential diagram. So at equilibrium, we have the N-type potential higher than the P-type potential by the contact potential, right, V naught. When you apply forward bias, you decrease the difference in potential energy, okay, so by V naught minus Vf. In other words, to think about this is that, recall that the holes are over here, okay? This is a potential barrier for the holes. coming this way because potential is defined in terms of positive charges. When you apply a forward bias, you're decreasing that potential barrier, which means you're allowing the holes to go from the P to N, which is another way of saying what I just said before. When you apply a field like this, it's forcing the holes to go this way. You're reducing the energy barrier for the holes to go this way. Okay? The opposite for electrons. Of course, electrons flow down, right? In this particular case. We'll understand it better when you look at the energy diagram. For reverse bias, the opposite happens. You increase the potential difference. So you're increasing the potential barrier, okay, by VF in this case. Okay, or VR, actually. This should be VR. Okay. So the basic assumptions, just to reiterate, which I said, these are the same things I said before. The underlying assumption is that the applied voltage appears totally across the transition region. Okay? This basically means that there is no potential drop in the regions that are neutral, the bulk regions of the P and the N type. So any potential you apply at the edges here basically appears across here. In other words, we are assuming that this part of the semiconductor material is a perfect conductor. Right? There's no potential drop. There's no resistance to it. That's not strictly true. We'll come back to the assumption later on, but that's the assumption. It's a reasonable assumption as long as these regions are very heavily doped. If you have enough carriers, it's a very, very good conductor, then it's a good assumption. Okay? There's no voltage drop in the bulk regions. This is only really true when the bulk regions are very heavily doped, low resistance. That's a reasonable thing. We'll come back to that later. Okay, we'll show that that assumption actually cannot be true in principle. Okay, so from here you can deduce, looking at the potential, of course you can deduce the field, how the field changes and how the transition region changes in width, right? Because if the potential decreases, the field decreases. Okay, and the transition region also decreases because you have charge injection. There are fewer uncompensated carriers. Same thing happens for the reverse bias. The opposite happens. Okay. Of course, energy bands are probably the most instructive, and this is what you really need to understand, in my opinion. At equilibrium, of course, we know this very well now. Your conduction band that bends by the contact potential, we know. Valence band bends by the same contact potential. The Fermi level is constant. Okay. Under forward bias, remember now we have a potential difference. So the Fermi levels actually don't need to be constant. It's not equilibrium anymore. Okay, and this is an important concept which we didn't really cover earlier, but you can have splitting of the Fermi levels. Okay, so when you apply a potential, forward bias potential, the bending of these bands is decreased, as you can see. Okay, so the consequence of this is interesting because let's look at the holes for a second. The holes are in the valence band. Okay, this is an energy barrier for the holes, right? The holes are trying to go from here to here, but this is preventing it from going. Remember, this is electron energy, so hole energy is increasing downwards. Okay, so this is an energy barrier for the holes, and here you have decreased the energy barrier by the applied voltage. So you're allowing more holes to go through, which is what I said before. Okay. For the electron picture is actually easier to understand because electrons are going from this side, from the conduction band, to this side, from the conduction band. And this is an energy barrier. It needs to go up in energy, right? It doesn't like to do that. So, but by decreasing that barrier, more electrons are able to do that. And recall that it's a thermal distribution of electrons, right? Remember a long time ago we talked about the distribution of electrons which occupy the energy states. And there's a tail of them which end up in the conduction band. And if you reduce that energy barrier, more of them can actually go across from the N type to the P type. Okay? So in the forward bias, we make it easier for the majority carrier on one side to go to the other side. That's the way to think about it. Okay? When you apply forward bias, they make it easier for the holes from the P type to move from the P type to the N type. Okay, same thing. We also make it easier for the electrons to move from the N type to the P type. So you can generalize it by saying that you allow the majority carriers to go from one side to the other side. When you do reverse bias, the opposite happens. You prevent the majority carriers from going across. So you increase the energy barrier. So holes are unable to go across, electrons are unable to go across. Now you can get an intuitive feeling for why this is important. This is a diode, right? This thing is now, if I take these two pictures and put them together, this is nothing but, oops, that, right? You've seen this before, sister diode. You take these two pictures, it's just that, right? If I apply positive voltage, it's easy for the current to flow through. I've decreased the energy barrier. If I apply negative voltage, it doesn't allow the current to flow through. I've increased the energy barrier. Okay? So now I have a device which acts like a diode, but this can now be integrated onto a silicon wafer as opposed to a conventional vacuum diode. That's the whole revolution of integrated circuits. This is basically the picture. Okay? You see that, right? These things can be integrated into very, very small distances. This can be, hundreds of nanometers, or even smaller, like tens of nanometers. So you can have billions of these on a wafer. Okay? That's the picture. Okay, so the energy barriers reduce, carrier flows easier in forward bias, energy barriers increase, carrier flows harder for reverse bias. So the important thing also is the Fermi level. Now the Fermi level is split, and we'll come back to this. They're separated by the same amount of applied voltage. Remember, when no voltage is applied, the Fermi level is constant. When you have an applied voltage, the Fermi level splits on both sides, and it gets separated by the potential that you have applied. Okay? So when you have reverse bias, it splits that way. If it's forward bias, it splits up. Okay? And we will see why that's important in a few minutes. But recall that the Fermi level determines the location where you have 50% probability of that energy level being occupied. Right? So if the Fermi level moves, that suggests that the carrier concentrations have changed. Right? So think about what the Fermi level means. Okay? The fact that the Fermi level here is constant, but the bands have bent, suggests that the concentrations are different on either side, right? So here we know that's p-type because the Fermi level is close to the valence band. Here we know it's n-type because the Fermi level is close to the conduction band. But if the Fermi level itself moves, again, by looking at the difference between the Fermi level and the valence or the conduction bands, you can tell what the carrier concentrations are. And they have changed because of the applied bias. One would expect that, right? It's common sense. You would expect carriers to move and the carrier concentrations to change. Okay? And that's what we will calculate. And it's a little bit abstract, so you need to go back and think about this a little bit. It's a bit harder than what we have seen so far, but you can figure it out. Okay? The other assumption essentially is that we assume that the Fermi level far from the transition region is the same as that at equilibrium. So this Fermi level here is the same as the one there, and this Fermi level here will be the same as the one there. But the whole energy level has shifted. So the reference of energy has shifted on each side because of the applied voltage. Okay, we'll see what that means. Okay, of course, our goal here is to be able to calculate current, right? So again, going back to this picture. So remember, when you had diodes, you connected lots of diodes and you were able to build circuits, right? So resistors, diodes, capacitors, and inductors, you allow you to do all kinds of interesting circuits. But for a diode, the big question is, what is the current for a given voltage? Right? How does the current vary as a function of voltage? An ideal diode, of course, is that it is zero when voltage is less than zero, current is zero, and it's some value when the voltage is greater than zero. That's an ideal diode, but it's really never the case, right? You have a real diode, it's a little bit different than that. So that's the goal. I told you that the PN junction is a diode. The next question is, what is this for the PN junction? Okay? We need to know that in order to be able to design good devices. Okay, so let's look at it qualitatively first. So remember, first of all, that the diffusion current is due to majority carriers. Electrons from the N to P overcome the energy barrier, or holes from P to N overcoming the energy barrier. Okay? So remember, the diffusion always goes from high concentration to low concentration. So high concentration of holes, low concentration of holes. That's the diffusion current. But the key is that once the holes get to this side, they become minority carriers. Right? Now what happens to the holes when they get to the N side? Say that again? The drift, the potential, the field will try to pull it back. That's exactly right. In the depletion region, the built-in field will try to shoot it back. That's exactly right. That's why the diffusion and drift are balanced under equilibrium. But now we have shifted the equilibrium, so some holes are able to get across. So imagine the holes got across. So there is no field outside. Okay, that's the assumption. So once they have crossed that energy barrier, you reduce the energy barrier, so many holes have gone across. So what happens when they get to the N side? So there's holes that got into an N side, N-type material. What happens to them? Yeah?
I can't imagine they'd last very long without being filled by electrons.
Yes, exactly. They will recombine, right? So if there are a few holes and lots of electrons, they will recombine really fast. But not only that, they will diffuse, right? Remember we talked about steady state current injection. They will also diffuse. They will also move. Okay? And this has to do with the concentration gradient. So you'll end up with lots of holes right at the junction, right after there, and very few holes far away, so they will diffuse. Okay? But as they diffuse, they will recombine as well. And that's the current, right? That diffusion is the current. The diffusion of the minority carriers, which actually came from the other side. And the equivalent thing happens for electrons. For electrons, again, we reduce the energy barrier here by applying the forward bias. So the electrons go across from lots of electrons on the N side. Let's say they somehow come across to this side because we've reduced the energy barrier. Okay? Once they get on this side, there are lots of holes, the electrons will recombine. But they will also diffuse because right at this junction, you get a high concentration of electrons. Now, far away from here, there's very low concentration of electrons, so they'll diffuse. Right? There's a concentration gradient, so they'll diffuse. But as they diffuse, they will also recombine. And that's the electron current. Okay, that's the electron diffusion current. So the diffusion current, the cost of the diffusion current is majority carrier on that one side injecting to the other side, and they become minority carriers on the other side, and then they diffuse. That's the physical picture that you need to keep in mind. Okay? And then we'll do that. So let's look at it qualitatively. Okay. So at equilibrium, let's recap. This is particle flow. That's current. The holes try to go from p-type. The p is on the left, n is on the right. So holes go from p to n. The current is in the same direction, p to n. The electron diffusion is from n to p. The current is from oh no, that's drift. Sorry. So the drift. The whole drift, of course, is in the built-in voltage, which is going from this way, in this direction, right to left. So the whole drift is in that direction, whole current is in that direction. These two cancel out. The electron is in the opposite direction. The electron drift, this is electron diffusion from N to P. Electron diffusion current is from this way. And this is the electron drift in the opposite direction to the field, from P to N. And these two cancel out. Okay? These two terms cancel out. These two terms cancel out at equilibrium. When you apply forward bias, you can see qualitatively what has happened. You have reduced the barrier for diffusion. Okay? So again, you've injected more holes from P to N now because you've reduced that energy barrier. So this current component increases. Okay? The drift doesn't change much, and we'll talk about that in a little bit, because the field hasn't really changed dramatically. It changes a little bit, but even if the field changes a little bit, there are no carriers here. Remember, the drift current is proportional to the carriers. Our assumptions are there's basically no carriers in the depletion region. So the drift current, or very few carriers, so the drift current cannot change dramatically. Okay? At any instant of time. So this pretty much remains roughly the same. So you can see that the overall hole current has changed, right? It's no longer zero. It's going from P to N, left to right. Same thing happens with electrons. What we have done is we have reduced the energy barrier for the electrons, so more electrons going from N to P, diffusing, and the electron current, of course, in the opposite direction, P to N, and the drift currents are about the same. Okay? So the total electron current actually increases from zero, goes from P to N. And of course, they are in the same direction as the total current is increased. So you can see, if I want to calculate current, all I need to do is add up all these components, just like we did before. Just for a regular, remember we did this for a regular semiconductor, no junctions or anything, just N-type or P-type. We added up these four components. Basically the same thing. As I said before, if you're able to do that, you can apply it to any device. If you're able to calculate current in a homogeneous semiconductor. Okay? Before we jump into the equations, I want you to be fairly clear on this picture. The picture is much more important than the equations, like I said, in my opinion. Okay? For reverse bias, the opposite happens. You can see that the diffusion current for the holes is dramatically reduced because you've increased the energy barrier. So the diffusion current decreases. So the drift current is about the same. Okay? The diffusion current for the electrons is also decreased. The drift current is about the same. So you can see that this is not a perfect diode, right? Why? Because there is current here. It's not zero. I applied negative voltage. I'm not getting zero current, right? They're not balanced. I'm getting a little bit of negative current. Right? So it's not a perfect diode. And we need to know this. Why? Because this tells me that if I apply a negative voltage here, it's not a perfect switch. I'm still getting a little bit of current in the opposite direction, which we will see later on is an extremely important factor in why your computer chips get really hot. When a transistor is turned off or slightly reversed voltage, you're still getting some current through, which is creating, of course, this is a resistor too, right? So as the current passes through, it generates heat. And it's expending energy and so on. So when people do low power electronics designs, they have to be very careful about how you design these things. Okay? And of course, the heat in chips and so on are a very important practical problem because you cannot, if you want more and more transistors in your chip to get more functionality, at some point you're just going to make it too hot. So you have to worry about these things. Okay. Nowadays, people try to, because they're at the limit of how ideal you can make these nowadays, they try to manage the heat. They try to get the heat out. So in addition to electronic designs, people also do thermodynamic designs. So it's an interesting field by itself. Okay. So the basic point is that in forward bias, as you can see, as highlighted there, the energy barrier is lowered, the diffusion current increases. In reverse bias, the energy barrier is increased, the diffusion current decreases. Okay. Now let's talk briefly about the drift current. The drift current, as I guess the same thing as I said before, is due to the minority carriers. Okay. So what does that mean? Let's make sure we are very clear on that. So the drift potential is, well, the field is this way, right? So the drift current is essentially any holes which are sitting here, which somehow entered the depletion region, will see this field and will get swept across. Okay? It will very quickly reach this side. So it will spend very little time here, which is why we assume that there are no carriers there because they don't really stick around there, they're swept out. Okay? So it's a minority carrier hole that causes drift current. Of course, that's a current, right? That created that current. That is this component here, right? That's these components. Okay. Same thing for the electron. If an electron, which is a minority carrier, somehow diffuses into this region, it will very quickly get swept across by the field. Okay. And that's a minority carrier drift current. Okay. That's this current right here. Okay. So the drift current is due to minority carriers, electrons from P to N, or holes from N to P swept by the field. Changing the field by a bias voltage doesn't change the current much. Okay. It only changes how fast they're swept across. The current is more dependent on how many carriers are swept across. This is a few small depletion region. Excuse me, I want to make sure that I'm taping this for a second. I don't know if I did this right. Yes, okay, good. Okay, so the point here is that if you change the field changes, of course, right? Remember what we said? When you apply the forward bias, the field decreases, the built-in field decreases. If you apply reverse bias, the built-in field increases. So field changes, but there are very few carriers there. So remember, drift current is proportional to the field and proportional to the number of carriers that are available, as opposed to diffusion current, where diffusion current is proportional to the gradient of concentration. Two different things, remember. Okay. So the current is more dependent on how many carriers were swept across, and this is very few in the depletion region, so we can basically say that the current doesn't change. Okay? The field, increase in the field only changes how fast they're swept across, like the speed, right? Remember, the drift current was something like, I don't remember the actual expression, but something like the field, the mobility, times the concentration, right? That's the force. Right? Something like this. So if you increase the field, of course, the current can increase a little bit. This is a small number. Okay? So the whole thing doesn't change very much. Okay? Same thing, of course, for electrons as well. So the drift currents are almost unaffected by the bias voltage. So if you look at the reverse bias situation, you will see why this is important. Okay? In the reverse bias situation, you can see the diffusion current is very low. You're basically kind of killing that by increasing the energy barrier. Right? You're decreasing the diffusion of the electrons, diffusion of the holes. So the only thing that survives primarily is the drift current. Is this component, right? It's just sweeping across. And that's the current which shows up here. And that's the problematic current typically. That's a current that shows up when you apply negative voltage to a diode. It's something you don't want. Right? Creates heat, all that kind of stuff. So you can see, can we do something to engineer it? So you engineer the drift current. You can play around with mobility, you can play around with the field, play around with the concentration, but not too much, I guess. Okay. Now, okay. So there's a nice animation which I'll show you in a minute. So I forgot about it. So first of all, another way to think about the diffusion is the following. You have within, okay, so let's look at the p-n junction again. Okay. P, then we have depletion region. So positive charges here, negative charges here, all that stuff. Okay, and lots of holes here. Okay, few electrons. But remember, because of thermal energy, within this region, there's always electron-hole pairs being generated, just from the heat, the room temperature. Okay, so if you look at the band diagram, the p-type material, you have valence band, conduction band, or thermal. Okay. At any instant of time, some electron here can get bumped up there. This becomes an electron, this becomes a hole. This happens all the time, right? Because sometimes this kT over Q can be close to the band gap. Right? Remember, that's the definition of semiconductors. You get some of this thermal generation. Now, if this electron-hole pair generation happens near the junction, so you have electrons, you have holes, you get lots of these near the junction, they can diffuse. Okay? So the electron in the p-type region can diffuse to the depletion region. Okay? Many ways can happen randomly if you're near the boundary. Okay? When that happens, it'll get swept down the barrier to the n side. This drift current is also called the generation current. Okay, you can also create this current. So this is the drift current we talked about before, but you can also generate this with light. So this is how a photodiode works. So recall, you can shine light here and increase the generation of carriers, which is how a photodiode works. So you have a diode, okay, you have some load here. If you have light coming in, you can increase the carrier generation here, and that will get swept across by the drift and create current. And this is a solar cell, right? A photodiode is a solar cell. It's mostly drift current. So let's take a quick look at this animation. I actually forgot what this was, but oops. Oh yeah. So here you can see, let me zoom out. Okay, this is also a nice website if those of you are interested. This is it's called pveducation.org, and PV, of course, photovoltaic, so they talk about the basics of photovoltaics, and a solar cell is nothing but a PN junction, so most of what we talked about here in lesser detail is here as well. But this is a nice animation which shows what happens. So you can see P-type, N-type depletion region, okay, and they're going to apply a voltage. So in this case, it's equilibrium. Not many carriers cross, okay? So holes come in here, they get swept back. The electron comes in here, they get swept back. Those are the majority carriers, okay? Totally, overall, the current is canceled. Okay. There's a moderate field here which balances the current. So you can see the electron diffusion goes this way, hole diffusion goes the other way, electron drift goes this way, and these two have to cancel, and these two have to cancel. This is what we saw before. So this is the picture I want you to keep in mind. So make sure you go back and think about this, look at it. Okay, now we will forward bias it, okay? So we forward bias, oops. Okay, so you see what happens? Of course you get current, so those are electrons. Holes don't go across through metal, right? Remember, holes are in the semiconductor. And we talked about that picture early on when we talked about this in semiconductor. But you can see what's happening here. You have, oops, you have reduced the field here. Okay, so you've reduced the diffusion barrier. So you can see that the holes here, once they enter here, they can diffuse across because you've reduced this built-in field. So diffuse across from the P-type to the N-type. Once the holes get here, they can diffuse to the terminal and recombine. Okay, once they get to the terminal, they will recombine with an electron coming in from the terminal. Okay, same thing happens for electrons. So electron comes from here, the majority carriers, they come here and they can diffuse across because the energy barrier has been decreased, and then they can diffuse in this region, recombining. Remember, that's a minority carrier. Once it gets to the terminal, the electron can go to the battery. So that's forward bias. And you can see the electron diffusion current has increased, the whole diffusion current has increased. The reverse bias, you get the opposite. Essentially, you increase this barrier, increase this field, so the diffusion currents are basically canceled or minimized, and the only thing that happens is drift. So if you watch here carefully, you will see sometimes that the electron will enter here. Sorry, you see, you have to see this electron. See, if you look at the minority carrier here, so electron from here, once it reaches into here, it gets swept across. And that's the off current. Okay? And the holes from here, if they reach here, they get swept across. That's the drift current. There's no diffusion current anymore. So you see the picture? There's very low current outside. Okay? So that's the picture I want you to keep in mind. Okay. I'll post a link to that so you can play around with it yourself. Okay. So the total current again is essentially the sum of all these terms. So under equilibrium, you add these two up, they're zero. So add these two up, they cancel out. Add these two up, cancel out. Under forward bias, you see that when you add these two up, there is a net current this way. When you add these two up, there's a net current this way. So overall, there's a net current in that direction, in the forward bias direction. The diffusion current is from P to N, the drift current is from N to P. The drift current is the off current, essentially. It's opposite to the applied voltage. Okay, so keep that in mind. Okay, so the diode equation, and we'll derive this in a few minutes, looks like this. So this is the picture. You have a PN junction. You apply a voltage V. What is the current that flows through? It essentially looks like that, which you might have seen before. Okay, you have some constant here, which is the generation current that we talked about, multiplied by a term here, e raised to qv over kt minus 1. V is the applied voltage. And if you plot it, this is what it looks like. Okay, when the voltage is positive, the current is high, it increases. It's pretty much like an ideal diode, except that it increases. And when the voltage is negative, the current is essentially zero. There's a small negative value, which is, of course, we now know is the drift current. Okay? And it's also called the generation current because this comes from the electron hole pairs that are thermally generated. Okay. So at V equals 0, of course, it's equilibrium. The two currents have to cancel. The diffusion current and the generation current have to cancel. The diffusion and the drift. Okay? That is 0. Now, the picture is, okay, so the reverse bias, almost no diffusion current. There's a small generation current which is independent of voltage because remember it just comes from the thermal generation of electron hole pairs. And drift current is less defined by the applied voltage, remember, because there are very few carriers in the depletion region. Okay? The applied forward bias increases the probability that a carrier can diffuse across the junction because it reduces the energy barrier. So again, we are just reiterating the same thing. Okay? And that gives rise to a diffusion current which is exponentially dependent on V. Now, the exponential dependence, of course, makes sense, right? Because the probability distribution, remember the Fermi distribution, has an exponential dependence on the potential energy difference. That is the probability that the electron can come across and occupy an energy level, right? That's where that comes from. And we'll derive that. Keep that in mind. Okay? The total current is given by that expression, which is also called the standard diode equation, where the I naught is the generation current. It is the generation current minus the diffusion current at equilibrium. That should be a minus, not equal. Okay. The current increases exponentially with voltage. Current here is very low. And you can understand this from the energy diagram, which again we should be very familiar with now. I'm reiterating this many times because it's a very important way to think about it. Okay? Under forward bias, let's look on this side, which is forward bias. The energy barrier is decreased. Okay? So by that amount, and you get easier diffusion of carriers, easier diffusion of the majority carriers from one side to the other side. That's the picture. When you have reverse bias, you've increased that energy barrier, which means that you're preventing diffusion of majority carriers from one side to the other side. Okay? Okay, now we want to derive that. We want to quantify this. And I told you what happens is carrier injection. In other words, what happens, so ignore this thermal generation for Henry. But what happens is essentially you have the holes, the majority carriers here, once they diffuse across, they diffuse through here. They become minority carriers, they diffuse and they combine. That process is called carrier injection. They're essentially injecting the majority carriers from one side to the other side, where they become minority carriers. Okay? That's the carrier injection that happens under forward bias. That's the main component of the current at the junction. Of course, there's hole injection and there's electron injection. Okay? Keep that in mind. Now, whoops. Nice. Okay, maybe I messed up the order. So the minority carrier concentration will vary with voltage. That's another way to look at it. At equilibrium, let's recall that the whole concentration on the P type divided by the whole concentration on the N type is proportional to the contact, is exponentially proportional to the contact potential, right? We applied this in our example we did last class, right? We applied this expression. In other words, if I can change the contact potential by changing the doping, right? Remember we talked about that? Okay. This is, of course, roughly the acceptor concentration. This is inversely proportional to the donor concentration. Okay. Now, when you have an applied bias, like I said before, the Fermi levels split, and the difference in energy between the Fermi levels is just the applied bias voltage. Okay? So with the bias voltage, the concentration of holes at this location, minus xp naught, divided by the concentration of holes at this location, which is at the edge of the n-type, so that's the minority carrier, is now proportional to V naught minus V exponentially. Okay? This is basically what I said before in terms of the depletion width, the total width, remember? And you just make V negative for reverse bias, the equation is the same. So you can see what happens is that when V is positive, this whole thing decreases. When that decreases, this ratio decreases, right? Which means that I am getting more holes on the n-type. I'm getting injection of holes from this side to this side. Okay? Yes?
Just to be clear, the V naught minus V, that V is VF, right?
Yes, yeah, the applied voltage, yeah. If it's forward bias, it's VF. If it's reverse bias, it's VR, minus VR. Okay? If it is reverse bias, this voltage increases, this ratio increases, which means that I have fewer holes that are injected across. Okay? So that's how you can quantify it. Okay? Pretty straightforward. So the excess carriers injected across the junction does not change the majority carrier concentration much. Why? Because there are only few of them that get injected. Okay? So we have few holes here that get injected to this side. Now, if you look at the holes that have been lost, that's small compared to the total concentration of holes here. So the majority carrier concentrations overall do not change much, because you're talking about orders of magnitude higher numbers. Okay? So again, to look at this, so you have concentration of holes here, which is equal to the PP, which is the majority carrier concentration in the p-type, which is about the doping concentration, okay, the acceptor concentration. Then the question is, so this is the coordinate system, x going this way, 0 is at the junction, xn naught is on this side, minus xp naught is on this side. Okay? So what is the concentration of holes at xn naught? Is xn naught by Pn is EQV or KT. So as V increases, this number increases. Okay? Sorry, it's xn naught over Pn, so it's related to the minority carrier concentration on the n side. So the opposite to what we said before. Okay? That's the applied voltage. So at forward bias, the minority hole concentration at the end of the depletion on the n side is dramatically increased, exponentially increased. So again, let's step back and think about what that means in a second. So look on the n side, right close to the junction, okay? If nothing happens, the concentration of holes there is very small, right? It's a minority carrier, it's a lot more electrons, very few holes. As you apply the forward bias voltage, what happens? Suddenly, you get a huge number of holes showing up compared to what there was before. Okay? That's the hole injection, and that's defined by this exponential equation. Okay? And of course, those holes show up because they're injected from this side. They diffuse from the p-type to the n-type. Okay? So that's the big change that has happened. Okay? And of course, they will diffuse into the n-type region, and that will create a diffusion current, which is the majority of the current. Majority of this current. This current on this side. Forward bias. Okay? And that's what we need to calculate. This is called the minority carrier injection. Okay, so again, the picture to look at is that the holes get injected from the p-type to the n-type, the electrons get injected from the n-type to the p-type, Under forward bias, there's a steady state injection of holes into the N region, electrons into the P region. And of course, we can calculate the excess hole concentration and excess electron concentration by looking at the applied voltage. So the excess hole concentration, delta Pn, which is the extra holes that have appeared on the N-type, is given by the holes at xn naught, that's right at the boundary, minus the holes that used to be there before the injection, which is Pn, which is just the minority carrier concentration of the N-type. Okay, this was constant, right? This is just a constant concentration of holes everywhere within the N-type before a potential is applied. Okay, and we can show that that is proportional to e raised to qv over kt minus 1 because why? Because this thing is just that first term, right, from here. Okay. So now you can see that is the excess hole concentration on the N-type. And of course, that's right at the boundary. So right at the boundary, you have a huge number of excess holes. But as you move away from the boundary, the excess hole concentration goes down, so they have to diffuse. They diffuse from high concentration to low concentration. Okay, there's nothing preventing them from diffusing. There's no built-in field. And that causes a diffusion current, which is what we will calculate. Okay? You can do the same thing for the electrons. On the other side, delta NP is essentially the same way, NP e raised to qv over kt minus 1. So it's essentially the electrons that get injected from the N-type to the P-type, and then they'll diffuse over here. Okay, that's the picture. Okay, so to calculate the current, so again, you can plot the concentrations as shown here. So let's look at the holes in the N-type. So this is the hole concentration, this is location, starting from the edge of the depletion region. Okay, that's 0. So it starts at some number Pn plus delta Pn. Okay, Pn is the original hole concentration in this N-type material, plus the excess holes that have been injected across, and then they diffuse. And we know from the diffusion problem that we have solved before that the solution is an exponential decrease, where how fast this decreases depends on the diffusion length. Okay, and this diffuses and recombines at the same time, right? Remember, that's the diffusion equation we solved before. The excess holes here will diffuse into the N-type material, recombining with electrons along the way. It will form an expression which looks like that. This excess number is equal to delta Pn times e raised to minus xn over Lp, where Lp is the diffusion length. Right? It's the average length before a hole diffuses, essentially. Okay? Now, the same thing happens for the electrons. So you can write Np plus delta Np. Np is just the minority carrier concentration of electrons within this P-type material. Delta Np is just the excess holes that have been, electrons that have been injected across. And it also shows an exponential decrease where the speed of this decrease is proportional to the diffusion length of the electrons. Okay? In this case, note the origins. Origins are at the edge of the depletion region, not at the junction itself. So it's just shifted. But the picture is the same. So the excess electrons here will diffuse into the P-type material over here, okay, recombining with holes along the way. If the N and the P regions are long compared to the diffusion lengths of electrons or holes respectively, then you can calculate the diffusion equation which we solved before. Okay, again, expression, as I said before. And delta NP, of course, can be written in terms of the applied potential, which we just calculated, is Np raised to qv over kt minus 1 times the distance. Okay, so now you have an expression for the excess minority carrier concentration as a function of applied voltage and a function of position. Okay, away from the junction. That's all you need, right? To calculate current, diffusion current. Remember, diffusion current only depends upon the gradient, right? How fast does the concentration gradient change? The concentration change. Okay? So now you know everything to calculate the diffusion current. Okay? So same thing for holes. That's for electrons. From this we can calculate the hole diffusion current in the N-type material. The hole diffusion current is given by, it's a negative sign because remember the holes diffuse from high concentration to low concentration. and the concentration gradient is negative, so you have to put the negative sign, minus QA, area of cross-section, dP, the diffusion coefficient, times the concentration gradient of the excess carriers. So it's d over dxn of delta P. So if you plug that in, of course, the position-dependent term is just that term, right? So it's an easy integral, easy derivative, so you can do that pretty easily. So you get something like that. Now, dP over LP, of course, this LP comes from the exponent, right? You can see that when you take the derivative, this 1 over LP comes in the bottom. dP over LP is nothing but the Einstein equation, right? dP over LP, the diffusion and coefficient and the diffusion length are related. Not by Einstein equation, sorry, that's the mobility. But we will relate that in a second. But in any case, you get an expression which looks like this. Okay? A is the cross-sectional area of the junction. So this is the diffusion current of the holes when a forward bias voltage is applied. Okay? And you can see it depends on how many holes have been injected across the junction, essentially, which is obvious. And it depends on the diffusion length. Now, the whole current can, of course, be related to the voltage, which is what we are interested in. We want to make this plot, right? We want to make this plot, current voltage plot. That's the goal. So we can relate the carrier injection to the voltage applied. Essentially, it's the exponential term, right? Okay, so you can see where that diode equation comes from, right? The potential comes again from the fact that it determines the probability that the carriers can be injected from the majority side to the minority side. Because remember, it's the energy barrier that determines this injection. Okay. So again, you can just plug in the expression for delta Pn from before, which is just this term. It's actually from here. Okay. You plug that in. Oops. And you get an expression like that. Of course, this is just the whole current from one side to the other side. The electron current goes the opposite way, but remember that overall current direction is the same, so you have to add them up. Okay. This is that. That's fine. So, okay, so the question was which direction is the electron current? So let's think about that for a second. The electrons are here, okay? They're diffusing this way. The current is the opposite way, right? That's why there's a negative sign there also. But the total current has to be added up and they're in the same direction. So overall they'll add up. Okay? The whole current is diffused, holes are diffusing from here. The whole current is in this direction, left to right. The electron current is from, electron flow is from right to left here. The electron current is from left to right. Okay? Oops. Wait a second. What is, let's see. Oh yes, so this is the ideal diode approximation which we talked about briefly before, but there's a term to it. It's called the Shockley ideal diode approximation. Essentially, it assumes that there's no recombination in the depletion region, which is a little bit obvious if you think about it because we assume there are no carriers there. So there are no carriers. There are very few carriers, a very little probability of recombination. In other words, any carrier that reaches the depletion region essentially gets swept across. So the electron injected here reaches here. That's basically the assumption. Okay, and the reason for this assumption is that there are no holes there to recombine with that electron. Very few holes. Okay, so that's the assumption. Same thing for holes. The electron which gets injected here, the holes that get injected here, reach here. Which is why when we talk about injection, we just go from one side to the other side. We don't really talk about the depletion region. If you recall, I just said it went across, right? That's the ideal diode approximation. Not always true. Now the total current is electron diffusion current here, plus the whole diffusion current there. The two components to the current, they both contribute. Okay? Again, let me reiterate this because this is kind of a little bit of an abstract concept. If you calculate the diffusion current at this location of the electrons, that will be the assumption here is that that will be the same diffusion current of the electrons on this location. That's the basic assumption. In other words, any electron that crosses this boundary from right to left will also cross this boundary from right to left. Okay? So to calculate total current, if you want to do this rigorously, I need to calculate at one location, I need to calculate the electron current and the hole current. Okay? But instead, what we will do is we will calculate the diffusion electron current here and the diffusion hole current here and assume that they are basically the same at the other location. Then we can add them up. Okay, that's what we'll do. Okay, so, okay, so that's what's shown here. You have the whole diffusion current at this location, okay, plus the electron diffusion current at this location. There's a minus sign because remember there's an up. The electron current is opposite to the electron flow. So we're just adding them up. Okay, and the fact, in reality, if you want to calculate current in a device, the current is constant throughout the device. That's the assumption. Okay, so in other words, if I calculate current at this location or at this location or this location, they should all be the same. Okay, but my assumption here is that I will calculate the electron diffusion current here, the whole diffusion current here. And my assumption is that the whole diffusion current here is the same as the whole diffusion current there. So I can just add these two up. Okay? You need to go back and think about that. It's a little bit of an abstract concept. But anyway, you can plug those in, you get a very simple expression, which is basically the diode equation. Okay? So the current is now dependent on this term here, some constant. Okay, remember these are all constants basically, they don't change, times an exponential term, which is our diode equation we saw before. I naught e raised to QV over KT minus 1. Okay, so essentially it tells us what the current will be for an applied bias voltage. Okay, so for reverse bias, it's exactly the same, except that now it becomes a negative exponent. So this term, if VR is much greater than KT, this term essentially is negligible compared to 1. Okay, that exponent can be neglected because it's very small. Then essentially, under reverse bias, then the current is just minus I naught. Okay, which is basically what we saw in that plot. Okay, we have an expression. This is minus I naught. And you can see it depends on the diffusion coefficients, basically, right? Okay, so if you look at the plot, which I saw before, this is the voltage, that's the current. You can have a generation current here, which is the first term here, and then they have an exponential term, which is defined by that part. Okay, the minority carrier concentrations are the most important thing that determine the current, essentially. To think about it, because remember, it's a minority carrier diffusion that causes this. And the reverse current, which is this part here, is determined by drift. And the drift is a minority carrier drift, right? It is the electrons on the p-type which, when they reach the depletion region, get swept across to the other side. That's a minority carrier drift. That's why it's small, right? That's why that number is small. If one side is heavily doped compared to the other, then the carrier injection from heavily doped region to the lightly doped region will dominate, which is obvious. What that's saying is that if Pn is much larger than Np, which means that the N-type material is much more heavily doped, then you can ignore one of these terms, right? Obviously, there will be much more injection from one side than the other side, so that's obvious. In other words, these two components, one of them dominates essentially. Okay. If P is much more doped than the N side, then Pn is much less than Np, then the current is dominated by the holes injected from the P side to the N side. This is also called a P plus N junction. Okay, and this is very common in real devices. It simplifies the equations quite a bit. Okay. Okay. I think we will stop here in the interest of time because I want you to think about that question. That was an exercise we will do on Thursday. Okay, so again, the problem set is posted, problem set 3, so make sure you look at it. The review problems are posted for Friday and next Monday. Next Monday there will be a special review session to talk about the midterm. And next Tuesday there's no class. Okay, keep that in mind. I'll post all this online. So.